It's Paul here with a short script designed to show you how a function from R2 to R can fail to have a limit as the point at which we're evaluating it approaches the origin. I'm going to want to draw some circles, so I use the Math23 library, which I installed in an earlier script. And I'm going to define a bunch of sequences that converge to the origin. I put 50 points in the sequence. If you want to play with this script, you can change that value. Here's the sequence 1, 2, 3 on up through 50. Here's a sequence of nothing but zeros. Here's a sequence of the reciprocals of the first 50 integers. Head gives me just the first 6, and you can see we've got 1, a half, a third. Here's 2 times the reciprocals, 2, 2 over 2, 2 over 3, and so on. Here's the inverse squares, 1, 1 over 2 squared, 1 over 3 squared. Here are the reciprocals with alternate signs, minus 1, plus a half, minus a third, and so on. Let's maximize the available real estate by setting tiny margins. And let's set up a plot that includes the origin with not too much space in the negative range. Here's a function that will plot a sequence of points, and next to some of those points show the value of the chosen function f. First I plot the points. Type equals b means I join these points with lines. PCH equals period means I use a small dot. CEX equals 2 means I double the size of that period so we can see it. And notice I can pass the color to this function. Here is something that, for selected values in the sequence, 2, 5, 10, and 21, prints some text showing the value of the function rounded off to 3 digits. Here's a function to clear the screen so I can get rid of old plots. And now we're in business. Let's test this with a function whose behavior we know, the function r that gives the square root of x squared plus y squared, just the distance from the origin. So I will do this with the sequence where x and y are both the reciprocals of the integers. I'll plot it in red. We move in along the diagonal line where y equals x, and sure enough, we get the distance from the origin at every point. If I choose y to be inverse squares, then my points lie along a parabola, but it's still true, the value of r is always the distance from the origin. Here's a way of getting the points to move in along a line with slope 2. So that was a perfectly good function. It has a limit of 0 as my points approach the origin, and it works for any sequence of points that approaches the origin. Now, here is one of the best known functions with no limit at the origin. You can see if you plug in x equals y equals 0, you get 0 over 0, and in fact there is no way of defining a value at the origin that will make this function continuous there. Here's why. Clear the plot, and we will move in along the line y equals x by using the same sequence for both x and y. You look at the numerator and see that y squared minus x squared equals 0, so it's no surprise that the function value always turns out to be 0. If, on the other hand, we choose 2 over n for the sequence of y values, then we move in along a line with slope 2. Y squared minus x squared is always equal to 3. X squared plus y squared is always equal to 5, rescaled. And so the ratio is always equal to 3/5. Already we see this function can't have a limit because the function values approach a limit of 0.6 along one sequence, approach a value of 0 along another. If I move in along a parabola, the function values are not constant, but they approach a limit of 1 as we get to the origin. In this case, the limit doesn't exist. I can use any two of those sequences to show that that's the case, but I can also show it with a single sequence. Here is a function x times y over x squared plus y squared. I will clear the plot, and this time I will use a sequence where the signs for the y-coordinate are alternately positive and negative, and you can see as I move in along that sequence, the function values are alternately plus 4 when y is positive, minus 0.4 when y is negative, and so the sequence of function values doesn't approach a limit of all. Now here's a very interesting function. You might think that if you got the same value on approaching the origin along any straight line, then the limit of the function values would be the limit of the function, but that's not the case, as you'll see with this function hh. I'll clear my plot. First, I will move in along the y-axis by using the sequence of zeros for the x-coordinates, getting a limit of 0. Then I will move in along a sequence of points where y is equal to x, and yet again, you can see the function values keep getting smaller and smaller. They approach a limit of 0. If I move in along with a line with a different slope, that's the case. But if I move in along points that lie on the parabola where y equals x squared by using the inverse square sequence for the y-coordinates, then for every point on that parabola, the function value is equal to 1/2. So think about this in terms of the epsilon delta definition of limit. In order for the limit to exist for any open ball of radius epsilon greater than 0, I have to be able to find values arbitrarily close to 0. I can clear the plot, and this time draw a circle of radius 1/4, and you can see inside that circle there are points on the parabola where the function value is 0.5. There are points along the y-axis where the function value is equal to 0. If I choose, for example, an epsilon of 0.4, then I lose, because if I think the limit of the function is 0, I'm stymied by the fact that I found points where the function value is 0.5, and drawing a smaller circle causes no improvement, because no matter how small a circle I choose, there are always points on that parabola where the function value is 0.5. Don't conclude, though, that just because a function looks like 0 over 0 at the origin, it doesn't have a limit. Here's a function which I've named ff, where the numerator is xy squared, the denominator is x squared plus y squared. I cannot plug 0 and 0 into that formula. Nonetheless, this function has a perfectly good limit of 0 as the points approach the origin. Let's try it along the y-axis. Let's try it along the line x equals y. Let's try it along a line with slope 2. Let's try it along that parabola. And in every case, you can see the function values get smaller and smaller as I move toward the origin. If I put a small circle around the origin, the function values inside that circle become nice and small.